In this video, we'll learn how to solve 2D kinematics problems for IB Physics SL. So I have the same 3 tips as the 1D kinematics problem. The first one, always start off with drawing a picture. The second one, write all known information from the problem in a chart. The third one, identify which formula you need to use to solve the problem. And for 2D, there's another tip, which is identify the information that corresponds to the x component and the information that corresponds to the y component. So a ball rolls off a 1.3 meter tall table at a speed of 2.1 meters per second. Part A, where will it land? So we could draw something like this for our table and show that it's 1.3 meters tall. Then we could draw a ball and then show an arrow because it's moving that way, and then label that it's 2.1 meters per second. Then we could draw dashed lines for its path. And then in part A, when it asks where will it land, it's asking how far from the base of the table will the ball be when it's finished moving, so over here. So we could draw a line like that and label it delta Sx. Now we could draw our chart with all our information. So our first piece of information is that it's a 1.3 meter tall table, and this is a y type of value, so we could label that in orange, say delta Sy equals 1.3 meters. Then our second piece of information is that it rolls off with a speed of 2.1 meters per second, and since it doesn't talk about any angles, we know that it's only moving horizontally at the beginning, so we know that that's an x value, so we could label that in green, so Vx equals 2.1 meters per second. Then we could say A is negative 9.8 meters per second squared, and what we want to find is delta Sx, but to find that we need to find time first. And so I labeled time in blue because time is both a y value and an x value. So the formula that we need to solve this problem is Sf equals Si plus Vit plus 1 over 2 At squared. And we could modify this equation for this problem by saying Syf equals Syi plus Vyit plus 1 over 2 At squared. And then delta Sy is the same thing as Syf minus Syi. So we could say that 0 equals 1.3 plus we know that the initial speed in the y direction is 0 because the initial speed is just horizontal, so 0 times time plus 1 over 2 times a, which is negative 9.8, times t squared. And I made the acceleration due to gravity negative because that'll make the signs work out and time will be a positive value. So if we solve that, we get time equals 0.52 seconds. So that's the first part to solve part A. And then to find delta Sx, we need to use the formula V equals d over t. And we could modify this equation for this problem and write Vx equals delta Sx over t. So we know delta, or velocity for x is 2.1. Then we're finding delta Sx, and then time is 0.52. So if we solve that, we get Sx equals 1.1 meters. So for the second part of the problem, with what speed will it hit the ground? So to solve this, we need to draw another little picture. So at the end of its motion, the ball is going to be down here. So we could show the ball and then draw all the components of its speed. So the horizontal component, the vertical component, and then the net component, which is just VF. And the vertical component is downwards because right before the end of its path, it's going downwards. So we could label this one as VYF and then label this as VX. And you notice that I never put it as VXF because the horizontal component of velocity is always constant throughout its path. So to find VYF, we could use the formula VF equals VI plus AT. And then we could just plug in our values. So we know we want to find VF, then we know VYI is 0, and then plus negative 9.8 times our time, which is 0.52. Then we get VYF equals 0 or 5.096 meters per second. And then we know Vx is already 2.1 meters per second. And then to find this Vf, we could use the Pythagorean theorem, because if we rearrange the vectors by moving Vyf over here, then we get a right triangle. So we could use the Pythagorean theorem. So we could say Vf squared equals Vyf squared plus Vx squared, and substitute our values. So Vf squared equals 5.096 squared plus 2.1 squared. So then if we solve that, we get 5.51 meters per second. So that's our answer for the second part of the problem. So problem number 2, a car drives off a 52 meter tall cliff and lands 42 meters from the bottom. How fast was the car moving when it drove over the cliff? So first we could draw our picture. So this could represent the cliff, and we could label it 52 meters. Then we could just draw a box for the car and then draw some arrows just showing where it goes. And then we know it's 42 meters away from the cliff, so 42. And the way we solve this problem will basically be the same way we solved the last problem. So we could just go ahead and draw our chart. So for the y values, we know SYI equals 52 meters, SYF equals 0 meters, then A equals negative 9.8 meters per second squared, VYI equals 0 meters per second. Then for our x values, we know SXI is 0 meters and SXF is 42 meters. And then what we need to find is Vx because it's moving forward and not at an angle. And to find that, we need to find time. So I could label that in blue because that's both an x and y value. Just draw an arrow like that. So we're going to use the same formula as the first problem. So SYF equals SYI plus VYIT plus 1 over 2 AT squared. And then just plug in our values. So we could put 0 for that, 52 plus 0 times time is 1 over 2 times negative 9.8 t squared, and if we solve that, t equals 3.258 seconds. And then to find our speed, it will be the same equation to find the speed. So Vx equals delta Sx over t. Vx is what we're trying to find. Delta Sx is 42 meters. Then time is 3.258 seconds. And Vx equals 13 meters per second. So that'll be our answer for that. Number 3. A football is kicked with an initial velocity of 35.1 meters per second at an angle of 42 degrees. Part A. How high will it get? So we could draw a ball and then a line showing where it's going and label 35.1 meters per second. And then we could draw its components of velocity like this and label this Vx and Vyi. Then we could draw its path like this, and then when it asks how high will it get, it means its maximum point, so like that. And then before we draw our table, we should first find our components of velocity, so we know it's kicked at a 42 degree angle. So, and if we rearrange the y component of velocity to be over here, we see that it's a right triangle, so we could use sine, cosine, or tangent to find these components. So for Vx, we could say Vx equals Vi times cosine theta, because cosine is adjacent over hypotenuse. And then we could plug in Vi equals 35.1 times cosine 42. Then we get that to be 26.08 meters per second. Then we could do that for Vyi too, but we just use sine instead of cosine. So Vyi equals Vi sine theta. And then just plug the same numbers in, and then Vyi equals 23.49 meters per second. Now we could draw our table, and we could start off with our x components this time. So we know Vx equals 26.08 meters per second, and then we know that our starting x position is 0 meters. And that's it for our x components. So now for the y components, we know Vyi is 23.49 meters per second. And then Vy at the top of its motion is 0 meters per second, because every projectile for a moment stops at its peak. So Vy equals 0 meters per second. Then A equals negative 9.8 meters per second squared. And Syi is 0 meters. So what we need to find for this part is Syf. So we could use the formula Vf squared equals Vi squared plus 2a change in d, and we could change this for this problem by saying Vyf squared equals Vyi squared plus 2a, and then instead of delta d we could say delta Sy. So then we could plug in our values. So Vyf is 0, Vyi is 23.49, then squared, plus 2 times negative 9.8 times delta Sy, So delta SY equals 28.2 meters, and that's our answer for the first part. So for our next part, we want to know how long it's in the air, and we wrote all our quantities that we know. So for our wanted spot, we could just say, for part B, we could say time and write hang for the time. And then to solve for our hang time, we could use the formula VYF equals VYI plus AT, and I adjusted it for this problem already. And then we could plug in our numbers. So VYF is 0, VYI is 23.49, and then minus 9.8 times time. Then if we solve that, we get 2.4 seconds. But this time is our rise time because we put the final velocity as 0, which means that it's the time that it takes to get till this point. So to find our hang time, it would be 2 times the rise time. So 2 times 2.4, so the hang time equals 4.8 seconds. And for the last part, where will it land? It's basically asking for the horizontal displacement from this point to all the way here. So we could say it's delta Sx. So we could just use the simple formula Vx equals delta Sx over time. And then for this problem, we'll be using hang time because it needs to get from the starting position all the way to the ending position. So Vx equals 26.08 meters per second. Then delta Sx over the time, which was 4.8 seconds. Then delta Sx equals 125 meters.